Alright, so this question, a very long non-conducting rod. So there's some kind of rod here. And it's very long, so it probably goes, infinitely both ways. It has a radius of A. So this is radius of A. Has positive charge distributed throughout its volume. So there's charge, everywhere. It's not on the surface. Because it's non-conducting. The charge distribution is cylindrically symmetric, and the total charge per unit length of the rod is A. So if I take a unit of length, if this is unit of length X, and I look at all the charges within it, that total charge is A. And then use Gauss's law to derive an expression for the magnitude of the electric field outside of the rod. So Gauss's law is the field enclosed is equal to the charge enclosed over permittivity of free space. So magnitude of the electric field outside the rod. So if we create a Gaussian surface, which is also a cylinder, if we create this surface, and then the electric field will be coming out through the surface, magnitude of the electric field outside of the rod. So electric field times the differential, what is this called? Differential. Infinitesimal change in X is also known as dA is just an infinitely small piece of A that we integrate over. The charge enclosed is going to be the volume times the volume times so the question says okay, so we know that one piece is A. So if we have a surface, then we can figure out the charge enclosed. Okay, so E times the surface of what we have. If you think about the surface of a cylinder, let's see. Let's say this is R. Surface area of a cylinder is equal to it's basically the circle times the height of the cylinder, circumference of the circle times the height. Circumference is 2 pi r times h. So this surface here is going to be 2 pi r times the length of whatever we're looking at. Now the charge enclosed within this length L is going to be A times the length, because A is the unit, is the charge for a unit length along the rod. So if we have this long, it's just going to be A times L. So we get this equals A times L over permittivity. So this is equal to, these L's will cancel out, A over 2 pi r. So that's the first step. And then, as the diagrams below represent cross-sections, sketch the following several equipotential lines. So here is the cross-section of the rod. Equipotential lines in the region R greater than A will look like this, because the potential will be the same around this circle. And then if I draw the electric field lines, they look like this. If the charge is positive, it'll look like this. Now the next one is in the diagram below, point C. So let's see. The diagram below, got a circle here. Here's point C, A, that's something like this. There's a 3A here. This is 90 degrees. So in the diagram below, point C is a distance A from the center of the rod. In other words, the rod surface. And point D, here's the point D, is a distance 3A from the center, that is 90 degrees from point C. Determine the following: the potential difference between points C and D. Alright, so we're looking for the potential difference, Vc minus Vd. Now we know that V is equal to the electric field times the distance. Sorry, the electric field is the potential times H, GH times R. So we have the electric field at these 2 points. We can find Vc. We know the electric field, and the electric potential is just the electric field times the distance A. So Vc is equal to A 2 pi r. Yeah. And then at 3A, Vd will be A 3A. So if you think of electric field as like gravitational field, electric potential is the work required to bring a test charge, to push a test charge through an electric field without causing any acceleration. The way I think of it, I think of E as pretty much the same as gravitational acceleration. And then we know that potential due to height is mgh, and when we look at the electric field, we kind of think of this as just the gh part of this, whereas the electric field times the distance. Now, of course, when the electric field is varying, you do need to integrate here. But at this point charge here, I believe we just multiply the electric field times the distance. And so Vc minus Vd would be this minus this. Negative AA pi r here. Now we think about this, the electric field at this point is stronger than electric field at this point. So it takes, when we're moving something from a higher potential energy to a lower potential energy, we're actually getting rid of, this is, kind of like something moving from the top of the mountain to the bottom of the mountain. So we are kind of like losing energy. So it makes sense for this to be negative here. So this is this. And then the question asks, inside the rod, the charge density is a function of radial distance r from the axis of the rod is given by rho naught r over a to the 1/2, where rho naught is a constant. Determine the magnitude of electric field as a function of r. Express your answer in terms of, okay, so this is just asking us to integrate the electric field as a function of r. So E equals 2 pi r. So let's say we have the cylinder here. Let's say this is our rod here. The total radius is A, but we're talking about another radius R of this cylinder within this bigger cylinder. Now, in order to, let's say our length is constant. Let's just set this as L, whatever. Doesn't matter. So the electric field enclosed, right, it's going to be here. The surface area of this will be for, what is it? 2 pi r times L equal to the charge enclosed. Okay, now so how much charge is in here? In order to find how much charge is in here, we have to integrate from 0 to r, where at each position of r, we're going to find the charge in that and the surface area of that cylinder. We're going to find the charge at each point here. Again, we know that this is 2 pi r times the length here. Times, so the total charge, right? The total charge is the integration of all these charges. So what we're going to do, dV, I can say this is dq, integration of all these charges. I can split up all these charges with different volume charges, in each one in like a concentric circle, like that. And to do that, it's just 0 to r. Times the charge density at each unit. Okay, yeah, this is the explanation. Let me rewrite this. So the total charge within this cylinder is the integration of all these infinitely small pieces of charge. The infinitely small piece of charge, when they add them all together, is basically equal to the unit charge density within this volume times whatever volume this charge is made up of. So this is a small charge volume, and we know that if we see this as kind of cylinder, where a small piece of volume is just this cylinder here, and we're just going to create this kind of like small shell here. This amount of volume is equal to 2 pi r L, because 2 pi r is the radius, is the circumference of the circle, times the length L over here. That would be the surface area times the a infinitely small change in radius. So this would be equal to rho r over a 1/2 times 2 pi r L dr, and then we integrate this. We can pull the constant out. So this is r over a 1/2, 2 pi, we can pull out L, we can pull out r dr. Let's see, this is same thing as this. So 1 over a r 1/2. So if we integrate this by parts, we say u is 1 over a r, then this will just be du equals dr. This will be, let's see, can I bring in the r first? So it looks like this, times r1, so I can combine these to be r3 over 2, right? And then I can pull this a to the 1/2 out of here, so then it's just r3 over 2. So the integration of this will just be 5 over 2, r to 5 over 2, 2/5 times r, 5 over 2, then I get 3 over 2, 5 over 2, 3 over 2. I believe it's just this. And we're integrating from 0 to r. So in the end, this is just going to be 2/5 r, 5 over 2, half L 2 pi rho naught 2 4 over so this would be L pi rho naught 4 over 5 r 5 over 2 a half, and then we have this 2 pi r on this side, so this goes down to 2, and then r minus 2, so this is 3, and then L is gone, so it's in a 1/2 rho naught r 3 over 2 times 2 over 5.